Hello there, and welcome back to the LabHub. So in this lesson, we're gonna learn the Kirchhoff's law and the RC circuits. So at first, let's learn this example. What is going on here? We got some loop, right? Some circuit. And here, the current goes from the positive direction for the resistor and ends up as a negative direction. Here's 20, here's a 10, right? So in that case, the voltage will be negative. And the opposite thing, if it goes through the battery, right, for some circuit, and the current goes from the negative charge to positive, from 0 to 12, the voltage will be positive. What does it mean? Let's try it on another example. The current in both cases goes in the same direction. But here is the opposite sides of the battery, the opposite poles. How can we estimate and how can we define what is the voltage in each case? We can use this tip. If it goes from the negative charge to a positive, the voltage will be positive. And if it goes from a positive to a negative, the voltage will be negative. Or just where it goes, it is. So it goes to the positive, the voltage is positive. It goes to the negative, the voltage is negative. So in that case, the voltage will be negative, and in that case, the voltage will be positive. This is the Kirchhoff's law. And also, just to memorize, 1 volt equals to 1 joule divided by 1 coulomb. It's necessary for many problems on Kirchhoff's law. Let's go further. The RC circuits. From the basic electricity course, we already know the law for resistors, the equation of resistors. So, resistors, if they located series, total resistance will be R1 plus R2, right? But in parallel case, it will be 1 by R in parallel equals 1 by R1 plus 1 by R2. But what about the capacitors? Because the RC circuits is about resistors and capacitors. And here is the absolutely opposite thing. For series, the equation looks like here. And for the parallel, so now let's learn an example of how does it works in a circuit. We got a currently open circle, they're not closed, with a capacitor. Here is some voltage, plus, 0, negative. So what is the current in that case? Yeah, since the circuit is open the current will be negative. Oh, the current will equal 0 because no electricity comes through it. Let's go further. Already closed circuit with the same capacitor, voltage positive and negative. So is the current is going on here? Sure, it goes. And therefore it means that the current in the circuit right now does not equal 0. And in that case, the capacitor fills up with a positive and negative charges. And a really important note, exactly for this example, switch closed just now. And here, switch open. Right? So here is just the moment when we closed this, when the electricity started going. But what about a long time later? It's still closed. Is there any current? No. Why? The current here equals 0 again because the capacitor has a gap here, right? So here is a gap. It fully filled up. So since the capacitor is filled for 100%, it's enough with the electricity. It can't pass more electricity through it. So here's the void. And no electricity going through the circuit. So the current equals 0 again. And, remarkable, later, a long time, when the capacitor is full, there won't be a current in the circuit because the capacitor closed it. Again, this is why the current equals 0 here. It's fully charged and created a gap. But what if we have both resistor and capacitor in the circuit? Right? So it's already closed. The current, the current is going. So what can be wrong? This is just the moment, right? So it goes, the current just started going, and the charge here can be estimated as this formula. Our voltage times coulomb. And therefore, after some time, right, we open the circuit. In one important note, it collected some electricity. We will use it later. So what's done? Is there any electricity? It depends if we ask where, because here the current equals 0. But here, since the capacitor collected some electricity and still holds it, the current here doesn't equal 0. And here's the resistor, right? And electricity passing through the resistor and going back for the whole circuit, And therefore, charge, like here, equals then the original charge of the whole circuit. Why? Because the capacitor collected everything. Everything got into capacitor, it collected, and now it throws it out. So then, charge equals to charge original RC. And what else can be estimated here is a time constant. This is a time needed to all the electricity disappear. Don't mix it out with the torque. This is the time constant, and it equals RC. And for this one, we need a graph. This is time. This is our starting point. Starting point, like the charge we started with. So when we close the circuit, or when we open the circuit, and the capacitor collects some energy, some electricity, it slowly but constantly fades away, right? From this point to this, and depending on the time. So it happens with a time constant that equals RC. And here, this is QO right? And if R in this equation is bigger, it takes longer to push all the electricity through the circuit and let the current disappear. What does it mean? If it equals, for instance, 8, we need to push it through the 8 resistance of 8 ohms to let it go through and finally disappear. But if it's 800, we need more power, more force, if we're talking about it and giving an example in more human way, right? If we give it more force, then it will go. Otherwise, if we keep the same force, it will take longer to push this resistance. So therefore, bigger resistance, larger resistance, doesn't matter, means more time to push all the electricity through it, because here is the wall of 8 ohms, and here's the wall of 800 ohms. And you are punching it. Which one will take longer to crack it out, to break it down? Of course this one, because it's just smaller than this one. And at the same time with the resistance. Imagine resistance as a wall. So the smaller the wall, less time needed to push all the electricity through it. And likewise, with a C, capacity, for capacitor. So less capacitor, less energy collected, right? We need to push through the wall. The faster it will pass through and finally disappear. So this is basically all I need to know about RC circuits, Kirchhoff's voltage law. See you next time. You are on a LabHub.